Let's discuss question number 28 from test 3. This is from vibrations and theory of machines. So basically theory of machines. Vibrations, we consider vibrations to be a part of theory of machines. So flexible rotor shaft system comprises of a 10 kg rotor disc placed in the middle of the shaft. So you have a 10 kg rotor disc placed in the middle of shaft, and the shaft is simply supported. Okay, 10 kg rotor disc simply supported. The dia is basically 30 mm, and the total length is basically 500 mm between the bearings. The bearings are simply supported, and the E shaft, basically the modulus of the shaft is 2.1 into 10 power 1 Pascal. The critical speed of the shaft is what is asked. Okay, so shaft is basically an elastic member. So when I have a shaft and I keep a mass, something like a rotor disc, it will bend because the shaft is elastic and it is something like a simply supported beam. So when I put a load P, which is equivalent to mg, there will be a deflection. Okay, so I can model the shaft, which is an elastic member. Remember, the shaft mass is neglected. Shaft is just considered as an elastic member. So I can just model the shaft as an elastic member. So it's less like a spring kept at the center, and you have a mass m, which is mg. So the deflection is, so this deflection basically comes from your deflection of beams. A simply supported beam and the load P is kept at the center, so the deflection is PL cube by 48 EI. Now this comes from the deflection of beams, and from this equation, when you apply this equation and on the one of the side and solve the integrate 2 times and solve it, you will get this deflection. So now you have a load mg, which is your P, and you're modeling an entire shaft as a spring where the deflection is delta. So I can find this stiffness, the equivalent stiffness, spring stiffness, which the shaft provides at the rotor end. So that is K delta is P, and P is mg. So K delta, and delta is your mg by K. My idea is just to find m by K. So m by K, or sorry, K by m, because so when I can model a shaft with this spring and K, the natural frequency is given a root K by m. Root K by m is my natural frequency for this system, natural in radians per second. So I need to get K by m. K by m is G by delta, and delta is my PL cube. G by delta, G is PL cube by 48 EI. Now P I can write as mg, so G will get cancelled, so ml cube by 48 EI is my K by m. So when I substitute this, my natural frequency is root 48 EI by ml cube. Now let's substitute these parameters and get a reasonable value. E is basically my N's modulus, which is 2, given as 2.1 into 10 power 11 shaft. I is basically, because this comes from, if you understand how this has come, I here is area moment of inertia of the cross section. For a shaft it will be pi by 64 d power 4, and diameter is given. Diameter of the shaft is basically 0.03 whole power 4 pi by 64 d power 4 area moment of inertia. Mass is 10 kg, length is 500 mm, so 0.5 whole cube. So when I solve this, I get a value 566 hertz, or 566, this is radians per second, the units. So I want a equivalent F, which is omega by 2 pi. So if I divide by 2 pi, 566 by 2 pi, I get a value in hertz, and that value is 90.15 hertz. Now this is my natural frequency. Remember, what we did is we modeled the shaft as an equivalent spring at the rotor end, and the deflection because of the load mg is given from, has come from deflection of beams. So if I model shaft as a spring, the natural frequency of this system is given as root k by m. So I'm just finding out the equivalent stiffness k and divided by m, and I'm getting this in term k by m for this shaft mass system. When modeled as a spring and mass, I get k by m as this. So I can just put this. So this becomes the natural frequency of the system. Now it is observed that when the the concept of critical speed is that, so when my shaft speed becomes your, shaft speed in terms of say radians becomes my natural speed, then resonance occurs. So that is the point when the speed of the shaft is called critical speed. So critical speed of the shaft in terms of hertz at the time of resonance is 90.15 hertz. So the answer is option is C. Thank you.